right, I'm going to do question 17 because this one was really badly done. Right, the circle C represents a locus of points. Right, now if you had a look in your notes or your revision guide or anywhere really, it would tell you that, well, not anywhere, it would tell you that the locus of points of a circle looks like this. Z minus x plus iy equals r. That is a circle with centre x, y and a radius of r. So if we get this z minus ai equals b into that form, then we can say, right, so we've got z minus 0 plus ai modulus of equals b. So in that case, sorry, that's a circle of centre 0, 5 and a radius of b. Okay, so straight away we know that a equals 5 if we compare those two things. Oh, by the way, where did the 5 come from? It's the midpoint of 2 and 8. Sorry, should have pointed that out. So the midpoint of 2 and 8 there is going to be 5. So a is 5. The radius of your circle, difference between 5 and 8, is 3. Okay, so moving on to the next bit, we've got a and b. Now this bit looks horrible, and I think this is what put a lot of you off. It's this bit here, isn't it? This arg z equals the inverse tan of k. Now, what on earth does that mean? Well, this half line down here, let's just get rid of that. This half line here is the line of all the points where the argument or the angle there is all the points that make up this line here, where the angle here is the argument of z. So say we've got this point here, P. What it's telling us is that the argument of z, so if we say the point P was 2 plus 3i, then the argument of that would be the inverse tan of the opposite over the adjacent. So in this case, that would be 3, that would be 2. Okay, so that would be the inverse tan. So the argument of P, that point there, the argument of 2 plus 3i is equal to the inverse tan of 3 over 2. But the half line makes up every single point, every single x plus iy that has that argument there, has that angle there, right? So that's what it's banging on about. Right, so we've got our triangle. Right, sorry, we've got our circle. That'd help once it's got the right shape. And we know that the argument of z is equal to the inverse tan of k. Right, now you need to be really cosy with your SOHCAHTOA and your Pythagoras and stuff to get this. Now, right, we're told that P is the only point that lies both on C and L. Now that's telling you that that's a tangent, so straight away we can draw in our right angle there, because a radius of a circle meets a tangent at a right angle. Then we can go ahead then and put in everything we know. So with the side of that, this side here is going to be 5, this side here is going to be 3. So using Pythagoras, we know that OP there is going to be 4. Just a straightforward right angled triangle. Right, then on to this business of this argument. Right, the argument of z. Right, so let's have a look at this right angled triangle here. Okay, now if we look at this line here from O to the set, or basically if we look at the y-axis, that's parallel to this line here that goes from the x-axis up to P. So we know that if this angle here, let's call it alpha, then that angle there is also going to be alpha. Okay? So let's call this angle here, oh, that's too fat, isn't it? Let's call this angle here beta. And we know that alpha and beta make a right angle because the angles in a triangle add up to 180 degrees. Okay, so by the same reasoning then, this angle here must be beta. And this is the argument of z here. This beta is actually the argument of z. It's this angle that this half line is making with the x-axis. Remember, we always measure angles from the positive x-axis anti-clockwise. Okay? Right, so looking at that top triangle here now then, we can simply read off from there that the tan of beta, which is the one that we're interested in, that's the argument of z, is the opposite over the adjacent. So it's 4 over 3. So tan beta is equal to 4 over 3. So in that case, beta is the inverse tan of 4 over 3. But as we've just discovered, beta here is actually the argument of z. It's the angle that z makes. So argument of z is equal to the inverse tan of 4/3. And so in that case, k must be equal to 4/3 if we compare those two things. Right, finally, we want to get to the point where we can find p. Now, we could do this in lots of different ways. We've got an equation of a circle here. We can work out the equation of that circle. If we want to, we can work out the equation of that line as well, because we know it goes through 0, 0, and we know, do we know what the gradient is? Well, we certainly know what the gradient of the centre to P is. So we know that the gradient of that line OP is the inverse reciprocal of that. So we could just use coordinate geometry for that, if we felt like it. Or again, we could use a bit of SOHCAHTOA. Should we use a bit of SOHCAHTOA? Yeah. Right, so let's look at that original right-angled triangle there. I remember trigonometric ratios are exactly that, they're just ratios. So we can read off the ratios for sine alpha, cos alpha, and so on from here. So sine of alpha is opposite over hypotenuse. Cos of alpha is adjacent over hypotenuse, and if we wanted to, we could do tan alpha as well, but I don't really want to do that. Okay, so what I'm trying to do now is I'm going to try and work out this side here. Let's call this is y. Okay, this side here, because I'm looking for this y coordinate of P here. How high up is P? So if we look at this triangle here with the side 4 and that side y, and this side here is alpha, and that there is a right angle. To find this side here, now this is all GCSE level maths, none of this is A-level maths, I would have said. I mean, the problem solving element is, but otherwise it's not. Okay, so to find y, we've got adjacent and hypotenuse, so that's cos. So cos of alpha is equal to adjacent over hypotenuse. Cos of alpha from up here is 4/5. So 4 times, bring that up, cos alpha is 4/5. We've got that y is equal to 16/5. Or you might like to prefer to write that as 3.2. Similarly, we can find the x value in our triangle. Why do I keep getting the wrong pen? We can find the x value here, this distance here, using the same methodology. So we want the opposite. We know the hypotenuse. We could use y if we wanted to, but if we'd made a mistake, probably best not to. So sine alpha is equal to the opposite, which is x, over the hypotenuse, which is 4. So 4 sine alpha equals x. Sine alpha is 3/5. So 4 times 3/5, 12/5, which is 2.4. So that tells us that P has coordinates 2.4, 3.2. Or if you've written it as a fraction, 12/5 and 16/5. Boom! So all that was just GCSE maths. Now, wherever you've got a right angled triangle, you can always do these ratios. Always, always, always. Okay, just bear in mind that doesn't mean that the side lengths are 3 and 5. It means that the ratio of the angle is 3/5. Okay? Right, hope that helps. Bye-bye.